About a year ago, I put out this video about perspective, and I thought I would review this because in part two, I'm going to show you an absolutely hilarious example of flat earth ignorance on this subject. The video started with this simple question: why do these parallel lines appear to converge? Now, flat earthers think you need a drawing that already shows these lines converging, but I say no, you need a scale orthographic view that shows the angular size changes. So let's see what caused this. So I'm backing away, turning 90 degrees to that railing, and surprise, surprise, it looks exactly like the orthographic drawing. And this makes logical sense because perspective is based on the actual sizes and distances of objects. So this was the location of my camera in that video. And the angular size of the first post in the orthographic view matches what my camera saw in reality. And since the second post was farther away, of course it had a smaller angular size compared to the first post. And not surprising, this matches the definition of visual angle. The visual angle is the angle a viewed object subtends at the eye, usually stated in degrees of arc. It is also called the object's angular size. And they include this graphic showing exactly how it works. And of course, a camera works exactly the same way an eye does. Now, since that second pole is farther away, both the top and bottom angles have converged to eye level. And this convergence continues with each pole as they get farther and farther away. So there are two different ways that we measure objects. First is the actual size that does not change with distance, and we have the angular size that does change with distance. And most importantly is that there is a correlation between that angular size change and the distance of the object. So I'll use this scale drawing of four 10-foot poles that are evenly spaced at 10 feet apart with a 5-foot eye level to show the correlation of the apparent size and the distance. This shows the difference of the angular size between the first and second poles. And the correlation is that the second pole appears to be half the size since it is twice the distance. And this correlation continues because it appears to be 1/3 the size at 3 times the distance, and 1/4 the size at 4 times the distance. And of course the fourth pole appears to be half the size of the second pole because it is twice the distance. Now if those poles continued off into the distance, eventually the angular size of the pole would be too small to resolve, and that would be the vanishing point. Now, since we know the height and distances of these poles, we can calculate their angular size with high school trigonometry. So in this case, for the first pole, we would divide it into two separate 5x10 right triangles and then use the formula below. Now, you can either do this with a calculator that has a trigonometry function, or use an online angular size calculator. And in this case, both of us give an answer of 53.13 degrees. So how can we use this knowledge in the flat earth globe debate? I used this example in my original video, which was a question posed by a flat earther. How is it possible the distant taller mountain would ever appear shorter than the smaller tree on a flat earth? Now this drawing showing angular relationships shows how it could be possible. But he continued with, perhaps when we omit the angular relationships showing only the absolute size relationships in calculations. And this is why flat earthers fail to understand how perspective really works, because those angular relationships are based on absolute size relationships in calculations. So here's an example of how these actual size relationships can predict exactly what we see in perspective. So I have four 16-foot poles spaced 16 feet apart. Over here I have a 32-foot pole at 128 feet, and I have an observer with an 8-foot eye level. So which of these 16-foot poles appear higher than the 32-foot pole? Well, the first thing I could do is just draw lines from the observer's eyes to the top of each pole, and we can see that the first two poles appear higher and the last two poles appear lower than the 32-foot pole. And I tested this with this scale set up using wooden blocks, and I had the camera's focal point set at 0 centimeters. This is a photograph taken by the camera, and as you can clearly see, the first and second poles appear higher, and the third and fourth poles appear lower than the distant 32 centimeter pole, which matches my prediction with this orthographic drawing, which is not surprising. So, will this also work with angular size calculations? So I'm going to start with the third pole, and an online calculator gives me an angle of 18.93 degrees. But we have a problem because these calculations are showing that the fourth pole should appear lower, not higher than the third pole. So what is going on? Now the calculation for the third pole is correct since it is an 8-foot eye level. But the calculation for the 32-foot pole is based on a 16-foot eye level. Now with the eye levels at the same height, these calculations correctly show that the distant pole appears smaller than the closer pole. So in order to do this correctly, we need to do this for right triangles that are formed above that 8-foot eye level. This is a 8 by 48 foot right triangle for the third pole, and the calculated angle above the 8-foot eye level is 9.46 degrees. The distant pole is 10.62 degrees above the 8-foot eye level, so these calculations correctly show that the third pole appears lower than the distant pole. Now here are the calculations for the first, second, and fourth pole. And of course they show that the first two poles appear higher and the second two poles appear lower than the 32-foot pole, which again matches what the camera saw. And in the real world, a surveyor with a theodolite would also measure these angles. Well, I think I've shown that flat earthers are wrong about perspective because they always want to pretend that the apparent or angular size of an object cannot be calculated based on that object's size and distance from the observer. But before I go, I want to answer this question. Are online calculators accurate for the flat earth globe debate? Because as I showed in my demonstration, when the objects are close, you have to be very careful how you set it up to get the accurate angular measurements. But in this debate, we're talking about objects that are miles away. So as I show in the example here, when the object is about 30 times its height in distance, then the angular size calculation is really going to be the same. I mean, in this example, the difference is 5/10,000ths of a degree, which is nothing. And this doesn't even change if the observer is at 1,000 feet instead of 0 feet. So yes, the online calculators are perfectly okay. I also want to show that the observer height is really not going to have much of an effect on these angular size calculations over long distances. So here I've changed the observer height to 5,000 feet, and again this is only 5.7 miles away. Now you can see that there's starting to be a greater difference in the angular size calculation, but both of these round out to 1.9 degrees. This will be part 2, and the answer is yes.